everybody. Let me turn the music down here. Welcome back to Chem 161. It is Wednesday evening of week 3. Some administrivia to go through before we get started here. Last call for worksheet number 1. The deadline is tonight. Make sure you get that in before the 11:59 p.m. deadline. The assignment will close at that time, and it'll just disappear, and you won't be able to submit your assignment, and I don't take it late. Quiz number 1 is due Thursday, so that's tomorrow. The quiz deadline shown on the screen is a soft deadline. You'll get a last call announcement on Friday, just in case you haven't done it. All of the quiz scores and results will be released after the Friday deadline is passed, so Saturday at midnight. I do have to hit a button, so if I forget to do that, or I don't do it fast enough, or whatever, send me an email. I will do that most likely on Saturday evening, because I'm usually up at midnight. But if I go to bed early or I forget or something, send me a reminder and I will unlock all the quiz stuff for you. Other than that, hey, it's chapter 2, some more of that. I think this section is mostly review. In section 2.4, we're going to get to some other stuff that isn't review, but also is old, I guess we'll say. So a lot of Chapter 9, Chapter 10, Chapter 11 stuff from 140. And then after that, we're going to hit Chapter 6. I don't think we'll get to Chapter 6 tonight. But we do the first 3 chapters, 1, 2, 6, because we'll get all the math out of the way in the class. And then it's just concepts for the rest of the quarter. You put your calculator away and you don't touch it. That's when we hit a little ways into Chapter 3. There's like 1 or 2 math problems in Chapter 3. Let's get started. So, we left off talking about the parts of an atom yesterday. We discussed where electrons were located in an atom and how they were discovered and their properties were assessed. We also discussed how the presence of a proton was determined beyond its charge. We knew its charge had to exist somewhere. We just didn't know what physical entity it resembled. And that was through another experiment. And then we talked about neutrons. We didn't really go into much detail about the experiments there. Today we're going to symbolize all of those things into some terms that you've seen. You're probably familiar with isotopic notation numbers. Let's go over all the components for that. So the first thing we're going to talk about is the atomic number. The atomic number, which was shown on the periodic table as an integer. So here's an example of that, or over here, or maybe up there, whatever. The atomic number is the number of protons an atom has by its definition. So if you are an atom that has 35 protons in its nucleus, doesn't matter what the rest of it is. You can have any number of neutrons, any number of electrons, whatever. If you have 35 protons in your nucleus, you are bromine. Congratulations. If you have 49, you are indium. And so on and so forth. Every single combination of protons has an identity, all the way up to 118 so far. Most of them have names. Some of the ones at the bottom of the table do not have names that have been assigned to them formally, depending on the periodic table you look at. I think that all 118 have been proposed to have names. I don't know if they have been made official yet. That seems to be just like trivia to me, but just in case you're curious. There's other piece of information on the periodic table we're going to care about. So the symbol, obviously, that's important to us. This number on the bottom, the atomic mass, we're going to use the atomic mass when we start calculating the average mass of atoms in the chapter later today. And then that number is going to become relevant for specific isotopes, which all have their own isotopic mass. The units of atomic mass are in atomic mass units. This is just a unit that we made up. We'll talk more about that when we talk about mass spec in a little bit. All right. Nothing super exciting here, so let's keep going. Now, if we don't have the same number of protons and electrons, we get an ion. An ion is any combination of protons and electrons that isn't equal. Depending on the direction you go, more or less electrons, you get a different type of ion. Strictly speaking, for a given element, you can't change the number of protons. That's fixed, because if you change the number of protons, you would change its identity. And also, it's very, very hard to manipulate protons without, as we discussed yesterday, shooting an atom into a super collider and watching it break into 1,000 pieces, many of which would be smaller atoms with some number of protons in them. So what we're going to do is we're going to just change the number of electrons, either up or down. If you have more electrons than protons, you're going to have a negative charge. And if you have less electrons than protons, you're going to have a positive charge. There's terms that we assign to these. Anion is any ion with a negative charge. Cation is any ion with a positive charge. The note that I want to be explicit on is that when you are doing math with these, remember that electrons are negative. When you subtract negative numbers, what happens? Well, the result gets bigger, right? 3 minus negative 2 is 5. So if I had a charge of plus 3 on something, and I remove 2 electrons, its charge would now be plus 5. The signs work the same way the math works. So be careful that you aren't accidentally doing subtraction and saying, oh, okay, I'm going to take away things to make it negative. And it doesn't work like that when the thing you're taking away is negative. So be mindful of that. On these slides are some examples. We don't really need to go over these in much detail because I'm sure that people have seen the conceptual form of how ions occur in previous classes. But just the short version is, if I have the same number of protons and electrons and I modify it, I get my ion. The interesting thing on this slide here is going to be this electron cloud that we've drawn. So here, oops, sorry, that's the wrong pen. Here is the electron cloud. And you'll notice that when we remove an electron, the electron cloud gets really tiny. And as you keep removing electrons, it will get smaller and smaller and smaller and smaller. We're going to talk about that in more detail in Chapter 3. So just sort of keep that information in your back pocket. If I add electrons, the opposite happens. So adding electrons expands the cloud. Now, it will keep expanding the more and more electrons that you add. We're not going to worry about which ions are stable just yet. We're going to deal with that in the end of Chapter 3 and the start of Chapter 4 when we talk about electron configuration and things like that. But for now, these two truths are relevant to our discussion of ions. And we want to note that the effect on the electron cloud is significant for later. Now, generally speaking, the elements that form cations and the elements that form anions are different. So metals tend to form cations. Non-metals tend to form anions. There are elements that are sort of in the middle that tend to do both. So, for example, carbon is sort of between metals and non-metals. Carbon likes to do all sorts of crazy stuff, including not giving up electrons at all or giving them up partially, etc. There's a whole field of study dedicated to that, and if you are a biologist or a biochemical engineer or anything along those lines that involves biology, really, you're going to get to take organic chemistry. Hooray! Which is the study of chemistry containing carbon. There is so much there that we have a whole year of it for you. I personally love organic chemistry. I think it's super exciting, but it is very difficult. Ions have different electron configurations than neutral atoms do, and as a result, they tend to behave differently. If I drop potassium in water, it explodes, but if I drop potassium ion in water, Nothing happens at all. In fact, the result of putting potassium metal into water is the potassium ion. This has to do with the number of electrons that these elements or ions have. There is a particular stability in various configurations, and atoms will try to get to that. We're going to talk about that again in Chapter 3. Here's the symbology that we're going to be using. So the number of protons is represented as Z. This will come up in Chapter 3 as well. And then the mass number, which is how many protons you have and how many neutrons you have added together, we designate that with A. Okay, so you got Z and A here. Z is by far the more common abbreviation. We're going to use that a lot later. A is kind of nice to know about, but as far as chemistry is concerned, A doesn't really have that much impact. So it's more of just a formality so that we can identify specific isotopes in case we needed to. And there are reasons to do that we'll talk a little bit about in mass spec, and then I'll talk a little bit about NMR and why that's important. But for the most part, we don't really care about the weight of atoms. We care more about their chemical identity. And again, just as a reminder, protons and electrons in a neutral atom are equal. So if you have a neutral atom, you know the number of electrons because you know its number of protons. Now, the mass number is going to be an integer. Let's write that on here. So Z and A, actually both of these, are going to be integers. They're going to be whole numbers, and they're going to be positive. You can't have a negative number of protons, and you can't have a zero number of protons. But the atomic mass, as we're going to find out, does not land on an integer value. In fact, almost no atom has an atomic mass that rounds to 0.00000. Some of them round to 2 decimal places, but very, very, very few of them do. I think like fluorine might, and maybe sodium. But almost all of them round to some sort of decimal. So that should be your first cue that the mass number can't be the same as the atomic mass in the periodic table. They are related, sort of. Like they round close to each other, but they're not the same thing. More on that when we talk about mass spectrometry at the end of today's lecture. What we're going to do is we're going to try and identify a few atoms by using this notation. We're going to use ZA, and then I'm going to add in an extra thing for the charge, because you're going to see charge come up all the time. Might as well talk about it here. So here's what we're going to do. The first thing you're going to do is for any atom that you are examining in the context, I have put this curly brackets E placeholder. You're going to delete that and write whatever the chemical symbol is for the atom that you care about. So if we were looking at silicon, you would write Si instead of this curly bracket E. Then in front of the symbol that you just wrote, you're going to put the atomic number as a subscript. Then you're going to put the mass number as a superscript. And then finally, after that, you can write the charge. The charge is a superscript, and it comes to the right of the atomic symbol. When you write the charge, you need to indicate the number and the sign of the charge, unless there is no charge. So if there is 0 charge, you just leave it blank. You can also write 0. 0 is typically used just for metals, because oftentimes metals form charged complexes. But in the event that they don't, putting a 0 might be important to indicate that, hey, this is something that happens. It's not common, but it does happen. Once you have all these things written, you get to celebrate. The symbol that you have written is called complete chemical symbol notation. You may also hear it as isotopic symbol notation. I write ZAE just to save characters when I do that. Let's do an example here. I'm going to write a carbon isotopic chemical symbol notation for this description. I want to have 6 neutrons and 8 electrons. in my description. So carbon has the atomic number listed on the periodic table. And if you have a periodic table, you can look that up. Turns out it's 6. A is the mass number. Remember that this is protons plus neutrons. So I would add those two numbers together. 6 and 6 is 12. So that's going to be my mass number that goes up here. And then looking at 8 electrons, I need to consider what the difference is between the number of protons and the number of electrons. So if I have 6 protons and 8 electrons, and I combine those two together, the result I get is -2. Positive 6 and -8 added together are -2. So I would indicate that like that. The convention is to write the number first, then the symbol. If you write the symbol first and the number afterward, other chemists will understand what you are saying, but they will laugh at you because that's not what you're supposed to do. So if you wrote C-2, you'd be like, they would make fun of you and say, oh, that's cute, you must be new or something like that. And we don't want that. So I realize that down here behind my face, you can't see the word neutrons. Looks like ootrons, but there's an N there. Just trust me. All right. So on the board, I have several different ions or atoms in some cases. What I want you to do is fill in all the blanks on the table and then write the isotopic notation symbol that matches the descriptions at the top. I have tried to write them in such a way that it's more of a puzzle. So I want you to decipher this and do the best that you can. When you're finished, let me know in the chat. It's hard to type isotopic notation symbols because you don't have subscripts and superscripts. You can try to answer the questions in the chat if you want to, but more importantly, just let me know when you're done. I'm going to give you about 4 minutes to do this, okay? I'll check back with you in just a second. Something I probably should have mentioned. If you do not have access to a periodic table and you are looking up one online, P-table is really good to have bookmarked, and just keep that handy. You're going to need that a lot in this class. We're going to rely on the periodic table pretty much from this point forward. So copy that link, paste it into your browser, and then bookmark that and just have it handy for like test and quiz time too. Let me know if you have any questions. About another minute, and then we'll go over the answers. All right, let's put all this information together. I'm going to start at the top. What atom has 7 protons? Well, I have a periodic table just on my desk here because this is kind of my profession. So element number 7 is nitrogen. So I'm going to write the symbol for nitrogen. Boop. There we go. 7 protons, so it goes in the front. You're going to notice that the number that you put as a subscript in the front and the symbol are always going to be the same. So, for example, you'll never do this, because 8 protons would not be nitrogen, it'd be oxygen. 8 neutrons, so A is the mass number. How many protons and neutrons? 7 plus 8 is 15. 6 electrons, 7 protons plus 6 electrons gives a charge of positive 1, which you could write as 1 plus, or if there's only 1, you could get away with just putting the symbol by itself. All right, for the second one, Z is 25. I got to find 25 on the periodic table. That's manganese. A is 55, so I don't have to do anything there. Just write the number. And a charge of 2 minus, so there you go. Ooh, that was easy. And then for this last one, the same number of protons, neutrons, and electrons. So I know that it's going to have a 0 charge. A is 36, so I got this, and that's it. Well, if I have the same number of protons and neutrons, then I know that this must be true, where X is the number of protons. And so the number of protons must be 18, which means that this atom is argon. And there's no charge, so I don't need to put anything up there. For doing the tables like this, I find it easiest to do the isotopic notation symbol last if I can. So how many protons does chromium have? If you look on the periodic table, it's got 24. 24 protons and a charge of +4 means there are 4 fewer electrons than there are protons. And now we can do the isotopic notation symbol. So chromium, 4 plus, protons 24, neutrons is 24 plus 27, or 51. Down here, I have very little information with regards to the identity, but I can tell the identity by looking at the number of protons. But element 16 is sulfur. Excuse me. And by comparing the number of protons and electrons, I can see that they are equal, so there will be no charge. I can now write my isotopic notation symbol. 16. 16 plus 18 is 34. We'll put that right there. Finally, down here, if I look up what element Ag is, that's silver. It has 47 protons, so easy enough. Its mass number is 106, so if I subtract 106 minus 47, because this is protons plus neutrons, and this is protons, what I'd be left with are neutrons. And so that should be 16 minus 7 is 9, 9 minus 4 is 5. And then I have 47 protons and 46 electrons. I have 1 fewer electron than protons. So I have a positive 1 charge. There you go. Those are the answers. Any questions, let me know in the chat. For the most part, when you have these problems on the quiz for Unit 2, you're going to have a bunch of fields, and you're going to have to fill the fields in with the correct number. All right. Let's talk a little bit more about isotopes. When you look at an atom, its identity tells you the number of protons, and if it's a neutral atom, the number of electrons will be the same as the number of protons. But the number of neutrons can vary. So neutrons don't carry a charge, which means that you can have any combination of neutrons that you want to, with some limitations. Because protons repel each other and neutrons hold the protons together, some number of protons is going to be required. So if you have too few neutrons, your atom becomes unstable, and then protons can't stick to each other. But if you have too many neutrons, you end up getting an atom that decays. It starts turning neutrons into protons and then spits out electrons. This is how you get beta decay when we were talking about nuclear chemistry yesterday. So there's a sweet spot where the number of neutrons needs to fall into, but that sweet spot can be very narrow or very wide depending on the atom. I'm going to show you a collection of boron atoms here. And if we were to count the number of protons and the number of neutrons, what we would notice is that, well, they're all borons, so they all have 5 protons. But by looking at the mass numbers here, I could find that this one has 5 neutrons, but this one has 6 and this one has 7. What this means is that if I have a collection of atoms, and they have the same number of protons, but different numbers of neutrons, or in other words, same Z, different A, then the collection of atoms are described as isotopes. An isotope is just a version of an atom with a different weight. And that difference in weight is because they have more or fewer neutrons in the nucleus. Now, for the purposes of this discussion, I should mention that electrons do have a mass, but there are electrons are so much smaller than protons and neutrons that removing electrons effectively doesn't reduce its weight to a level of precision that we can really detect. I think an electron is about 1/1800th of a proton, so you need 1,800 1,800 electrons or so to change the weight of an atom by 1 AMU. And typically speaking, we don't care that much down to that many decimal places. All right, let me clear the text here. All right. And so this slide just talks about what we just discussed. You can have any number of neutrons that you want. Now, our discussion earlier, when I said, hey, there's only certain arrangements of neutrons that are stable, includes the naturally occurring isotopes. Excuse me. Most elements have several naturally occurring isotopes. Some do not have very many at all. For example, fluorine only has 1 naturally occurring isotope. But almost every atom has at least 2. At least until you get, on the periodic table, all the way down to number 93, which is plutonium. Uranium is the last atom to have stable isotopes. After that, all of them are unstable, which means that no combination of neutrons and protons sticks together for the period of time that we define as stable. Stable generally means that the half-life of the substance is on the order of billions of years. Uranium-238, for example, the most stable isotope of uranium, I believe, has a half-life of 4 times 10 to the 9 years. We consider uranium to be the limit of stability, and anything less stable than that is considered to be unstable. Why did we pick that number? That's roughly the age of the Earth. Now, that's interesting to us because if something is roughly the age of the Earth, well, where did all of the matter in the Earth come from? Well, it came from stars exploding and then the matter that remains collected and all that congealed into the big ball of flaming rock way back that became Earth. Well, it's still there, right? All of those atoms that coalesced into form the planet are still here. They're on our planet. which means that if anything has an half-life that is short enough being less than 4 billion years, odds are by today it's gone. So there are a lot of isotopes that, sure, they existed when the Earth was formed, but they don't exist anymore because they have long since decayed away. Those isotopes include synthetic isotopes. Any combination of protons and neutrons is technically possible. But the only ones that occur in nature are the ones that were stable enough to stick around. How long have I been talking and been muted? Oh my goodness. Wow. Okay. Yeah. No, I noticed that I hit the button and I was muted. I've been talking this whole time. Yeah. You should be able to hear things now. How far did I go? Jesus. Okay. Hold on. Yeah, if you see me start drawing on the page and you don't have audio, say something immediately. That's my fault. Okay. We're going to go back. So I was here. I was writing the purple isotope part. Not that far. I might have hit something on my keyboard or something on accident. Because I just looked at it and I was like, oh, I was muted. Was I on this slide? Okay. So what I was basically saying on here was that if you have an isotope on the periodic table, such as plutonium, and you see that it's in brackets, I think it's not 224, it's 244, right? Yeah. what this means is that this is the most stable arrangement. So that's the mass number of the most stable isotope. However, the brackets themselves indicate that these are synthetic and therefore radioactive. Now, various isotopes exist. There are naturally occurring isotopes that occur on Earth. And the reason that those are naturally occurring is because they have half-lives, or they decay slow enough that they persist over the period of the lifespan of the Earth. So when the Earth was formed millions upon millions upon millions of years ago, not millions, I'm sorry, billions upon billions upon billions of years ago, and all of the matter from outer space coalesce into the Earth. So from supernova and stars exploding and etc. What ended up in the Earth is still here today. And therefore, anything that we can observe must have come from that event. So what that means is that any elements that are stable have been around long enough since that time to still persist today. So we consider those to be called naturally occurring. Anything that's naturally occurring has been around the Earth for at least 4 or 5 billion years, however long the Earth has been around. I don't know the number off the top of my head. Most atoms have multiple possible isotopes that are stable. And so that means that between like 1 and 10 combinations of protons and neutrons for a given element stick around for longer than 4 billion years. We consider uranium to be sort of the limit because uranium is abundant in the Earth's crust, but it is still radioactive because you could test that. You could put a Geiger counter up to a sample of uranium and it'll go off every now and then. The half-life of uranium is roughly 4 billion years. That's our line where we draw between naturally and synthetic. So if something is a synthetic isotope, then it is not around for long enough that we could dig it up. Any isotopes that were synthetic by today's standards did exist when the Earth was created, possibly, if their half-life wasn't that long. Or I'm sorry, wasn't that short. But by the time the Earth had formed and then we get to today, billions upon billions upon billions of years later, all of those isotopes that we call synthetic today no longer exist. They've decayed away. So you can create any combination of protons and neutrons that you want, and we'll call it a synthetic isotope. It's just that the half-life of that isotope might vary between, maybe it's a few days long, maybe it's a few hours, maybe it's a few microseconds long. So there are various durations of isotopes. You can look up these if you'd like. They're on what is known as the table of the nucleides. And they list every possible combination of isotopes that have been both synthesized and detected. You could theoretically synthesize anything you want, but if you can't detect it, there's no good. Or there's no point, right? Alright. On this slide, we talk about how this number is obnoxious, and I don't want to deal with it, because that is such a tiny number. So instead we use atomic mass units, where the mass of a proton and a neutron have a mass of roughly 1 for a first-order approximation. Now you're going to see that the mass is actually a little bit larger than 1. We're going to actually care about those decimal places when we add like 40 or 50 protons together, or even like 10, really. Because we're going to end up in the hundredths place or so, and you can see that on the periodic table that you're probably looking at, many of those numbers go to the hundredths place. So having all of this information handy is very useful. And knowing the mass of something down to that level of precision is important. Now, in a previous class, such as 140, we just waved our hands and said, oh, a proton weighs 1, and a neutron weighs 1, and an electron weighs 0, and that's good enough. For our purposes in this class, when we're calculating molecular masses, we're going to want more decimal places. And so we're going to include those extra decimals. Now, how the heck do you get these numbers? How did we learn that a proton weighs this and a neutron weighs that, and so on and so forth? Well, we have a tool that we use for that. And where is that tool? I'm going to skip ahead to show it. There it is. So this tool is called a mass spectrometer. A mass spectrometer determines the mass of a sample based off of a definition. And the definition that we use is the following. An atom of carbon-12 has an atomic mass of exactly 12 AMU. So this is a definition, which means that it has an infinite number of sig figs, 12.00000000 forever. What we did was we put a sample of our carbon into the mass spec. And when you put it in the sample feeder, what ends up happening is it gets bombarded by electrons. And those electrons either stick to the atom or knock other electrons off. In either case, you create an ion. And I'm going to call that C star, because I don't know what charge it is. It should probably be positive. Then what happens is you're going to launch it through a field at a specific speed. Whee! And then you're going to pass it through a magnet. We learned that charged things bend in the presence of magnets, so it's going to bend at a given magnetic field. And what it's going to do is it's going to strike a detector. Now, the detector shown here is very large. Generally speaking, the detector is this little tiny aperture. And the detector itself sits behind the aperture, and anything else just hits this plate to deflect it. And so what we then do is, kind of like Millikan's experiment, we relate a voltage to a mass. And so what we can do then is we can say, okay, I'm going to calibrate this until I detect carbon-12. And so you spin the voltage until you get the beam to go right into the detector. And then you calculate that voltage to a lot of sig figs. You say, okay, that is 12 AMU. Now what you can do is you can change the voltage and figure out the mass of anything else. So now I could put carbon-13 in to the detector. And if I put it at the same voltage that carbon-12 hit the detector, nothing will happen. But then I can spin it a little bit and find, oh, okay, at this voltage, carbon-13 hit the detector. So now I can figure out its mass. And from there, we can figure out the mass of everything. Okay, so we're going to come back to mass spectrometry in a little bit, but this is how we get these numbers to a large degree of significant figures. And as you can see, we get those numbers to a high degree of precision. So, for example, if I put boron 10 in the detector, it tells me that I need 0.83442 times the mass of carbon-12, whatever that voltage equates to hit the detector. So then what I will do is I will say, okay, well, I will multiply the mass of carbon-12 by that number to get the mass of boron 10. So now I can get a very high degree of precision based on what values I get from this mass spectrometer. In other words, this is just a very, very, very fancy balance for weighing individual atoms. Because once we atomize the atoms in the ion field, they all fly through, and then they strike the detector one at a time. Not like 1 per second, but like quintillions per second. But we can see that, at least. Since they're all independent, they all get bent the same amount by the field. So now what we can do is we can calculate the atomic mass of virtually anything. And from that we can calculate the isotopic mass of any isotope we want. And from that we can determine the atomic mass, which is the number that we write on the periodic table. So there's these two things here. So isotopic mass is for a specific isotope. Averaging all of the isotopes together gets you the atomic mass. Now, in order to, I don't know if I put the formula. I don't put it on the board here. So I'm going to show you the formula for a weighted average. Actually, let's do that on this right here, because we're going to use this formula in a second. All right. How do you take the average of anything? Like if I had X and Y and I wanted to find their average, I would just do this, right? Or if I had three things, I would just add them together and divide by the number of things, right? Now, couldn't I instead write my average like this? Or maybe like this? Those are mathematically equivalent statements, right? I'm going to separate these out too. So the top stuff, those two are equal. And the bottom two, those things are equal too. Now, what we've done here is we have assigned each of the variables that we're looking at a weight. And for a normal average, they all have the same weight because they all contribute evenly. But if I want to find the average of something that isn't evenly distributed, for example, maybe I have 80% of one isotope and 20% of the other, I can't use this average formula. So what I use instead is a weighted average, where I would say, okay, if I want 80% X and 20% Y, then my average would be 0.8 times X plus 0.2 times Y, where these are my weights now. So the formula for weighted average is just this. I ran out of space. Let's go to the top then. So the weighted average is equal to how much of the first thing you have times the mass of whatever you have, and then the percent of what the second thing is times its mass. And you just keep doing this over and over and over until you've got all of them in there. You can put X's or Y's or 1s and 2s, doesn't matter. But this formula will tell us the weighted average of any arrangement of percentages and masses. For our exploration of this is going to be the percent abundance of isotope X mx will be its isotopic mass, and then this right here will be the atomic mass. X, Y, Z, W, N, whatever those are all going to be individual isotopes. So this is an isotope, this is an isotope, this is an isotope. So we're going to list all the natural isotopes. For whatever element it is we're looking at. And so that's how we're going to calculate it. So let's do an example here to show how we calculate the isotopic mass on the periodic table. That's not what I meant to do. I meant to do this. There we go. And then after we do this example, we'll take a break. We'll do another example. So from this data that has been collected for boron, let's calculate the atomic mass on the periodic table. Now, you could just go to the periodic table and be like, hey, it's 10.811. But we're going to show how you get that number. So here we go. So let's put all this information in the calculation. So I have 2 isotopes, which means I'm going to have 2 terms. And for those terms, I'm going to have the percent of the first isotope, which would be boron 10, times the mass of boron 10. And then we'll do the percent abundance of isotope 11, boron 11, times the mass of boron 11. And then we'll punch in the calculator and hit equals. So let's enter all those numbers. So boron 10 is 19.9% abundant. We want to write that as a decimal so that we don't have to deal with the units of percent. Times boron 10's mass, which is 10.0129 AMU. Boron 11 is more abundant, 80.1% abundant, so we'll write it as a decimal, times its mass, 0099, I can't read the number, 0093. There we go. And so now I just punch it into the calculator, but I have combined functions, so I need to do multiplication first, then division. So 0.199 times 10.0129. I get 1.9925671. I only get to keep 3 sig figs here. So this part becomes 1.99 AMU plus 0.801 times 11.0093, 8.818443. Again, only 3 sig figs, so I'm going to keep 8.82 AMU. Now I'm going to do my addition. Both of these go to the hundredths place. So when I add these vertically, like, say, this, I get to keep this spot, so I'm going to keep all the digits that come out of the calculator when I put them in the calculator. And I get 10.81. So that's the number I would report on the periodic table. And if you look at the periodic table, you'll realize that, wow, that is really darn close. And that's great. We like when things match up with what data we have, because that means that it was done correctly and also that we've done it correctly. Now, if I wanted more sig figs, I'd have to calculate the percent abundance to more decimal places. That's surprisingly difficult to do, it turns out, because for random samples, there tends to be some isotopic variance. You might think, well, wait a second, how can there be isotopic variance if all of these isotopes came around from the start of the planet being there? And the answer to that is, well, on the surface of the Earth, we are constantly being bombarded by subatomic particles from the sun. For example, the sun emits protons and neutrons and electrons and other subatomic particles at a staggering rate. Some of those particles get absorbed by the atmosphere, some of them get deflected by the Earth's magnetic field, others hit the Earth and affect the atoms that are currently there. And so there is a slight variation depending on exposure to the sun and other phenomena. So the reliability of the periodic table depends on what element you're looking at for the most part. For example, it's harder to get an accurate measure of the isotopic abundance of nitrogen because depending on where you take your sample from, if it's exposed to more or less light and subatomic particles, you could have variations there. And you can't just take from one sample. Like if I only get my sources from Mauna Kea or Mauna Loa or wherever the telescope is in Hawaii, where they do the CO2 testing, then I'm sort of biasing my results towards that. I want to know the actual average. Well, you take it from everywhere and then average that. So getting percent abundance to a lot of sig figs is not always possible. But we do the best that we can. When we come back, we're going to do more examples using this formula. But for now, please take a break. That's not a break. That's not a break. That's a break. All right. I'll hit the timer. I will put on more Metroid music. And I'll see you in 10 minutes. Close enough. Let's mute the music here. There we go. Alright, welcome back. We're going to go on to the next problem here. So, this problem that we just did is what I would call the simplest version of isotopic mass style problems. I give you the mass and the abundance of X number of isotopes, and you do the weighted average. Now, there is another type of problem that you can run into, and that is trying to figure out parts of either the mass or the percent abundance based on having a periodic table handy, as well as getting some pieces of information. So for this problem, we're going to need the periodic table. And so we've identified that there are two naturally occurring isotopes of chlorine, chlorine-35 and chlorine-37. Here are their masses. Determine the percent abundance. Now, in order to do this, we're going to have to do some algebra. So let me find this and this. That doesn't help anybody. There we go. All right. So I'm going to leave the formula up there, but I'm going to delete everything else down here because we're going to need all this space. In fact, I might as well just zoom out a little bit. All right. So we've got our formula there. So what I need to do is I need to write all the information that I have into this formula. So I need the atomic mass right here. Oops, that's not the pen. Well, I could just do this. I need the atomic mass right here of chlorine. So let's go to the periodic table. Actually, you know what? Let's not do that just yet. Let's just write this. So we're going to say M. It didn't work. Why isn't my pen working? Select all. Oh, because I have this teeny tiny area selected. That's why. So that is going to be our atomic mass of chlorines right there. So the mass of chlorine is going to be equal to the percent abundance of chlorine 35 times the mass of chlorine 35 plus the percent abundance of chlorine 37 times the mass of chlorine 37. Let's look through this expression and see what we know. So we already know this because it's off the periodic table. I know these two because they are in the problem description. So chlorine 35's mass is 34.9689. Chlorine 37's mass is 36.9659. But there's a problem. I don't know what the percentages are. And as far as algebra is concerned, you cannot solve one equation with two unknowns. I would need to either identify one of these unknowns or make a second equation. How the heck do I do that? Any ideas from the crowd? What should we do? What other information is available? So I already got the AMU of the periodic table. That's this number right here. So we have that one. That one's already gotten. We need other information. What do you think? I'll give you a hint. Think about the parts of the formula that are missing. What do they mean? And what do you know about them? I'll give you a hint. We're working with percentages, right? What does that tell you? So the problem is that we have one equation with two unknowns in it. I don't know the percent of chlorine 35, and I don't know the percent of chlorine 37. That would be like writing this expression like this. So some number equals x plus y, and then saying solve for x and y. You can't, right? Well, if we're working with percentages, what's true about two percentages if these are the only two entities? Like, say, maybe I took this number and I added it to this number. What do I have to get? Yeah, they have to equal 100%, right? There you go. There's our second equation. So if we take these two equations, now we can solve for pieces of information that we're missing. So now we can solve for these. What I'm going to do to make this a little easier to work with is we're going to replace these with variables. I'm going to call this guy X, and we're going to call this guy Y. And so now I have a bunch of numbers with X's and Y's in them. I can solve for X and Y, just like you did in Algebra 1 or 2. Yeah, it's super basic, isn't it? But you don't really think about it because it's not something that, like, why would we apply math? Well, it turns out we have to apply math once in a while. So we get solved for a two-variable equation. In fact, I'm going to show you how to do it algebraically and how miserable that is. And then I'm going to show you the easy way. So I need to move this a little bit. We're going to do algebra, and we are not going to do the numbers until we've got all of the algebra figured out. So what I'm going to do is I'm going to solve for x, which means that I need to rearrange equation 2 here. We'll call this equation 1. So that it's x equals something. So we're going to take equation 2. X equals 100% minus y. I'm going to write this as a decimal, because we've been writing all of our percentages as decimals for these problems. So let's just do that. Then we don't have to worry about a symbol, and I can write less numbers and so on. Everyone okay with that? So now what I'm going to do is, once I click on the screen here, we're going to substitute x equals 1 minus y into equation 1. And so that's going to make equation 1 look like this. The molar mass, or the atomic mass of chlorine, is equal to x, which is this right here, times the molar mass, not molar mass, I keep saying molar mass, the isotopic mass of chlorine-35, plus, we would say y, but we've substituted it. Oh shit, I did this backwards, sorry. I thought I was solving for y. Let me just do this again. Sorry. I'm substituting in x, so that means anytime I see an x, I have to write 1 minus y. Sorry, I can do algebra, maybe. Plus y times the mass of chlorine-37. There we go. That's better. I said I was solving for x earlier, and I jumped ahead in my head, so I solved for the wrong thing. Whoops! There you go. Now I have one equation with one unknown. This can be solved. However, we have to go through algebra hell to do it. So let's go ahead and do that. So I'm going to distribute this M chlorine-35 in this equation. So MCl equals MCl35 times 1 is MCl35 minus Y times MCl35 plus Y times MCl37. Then what I'm going to do is I'm going to isolate all the terms with y in it, so I can eventually factor out the y. So what that means is, because I'm not doing multiplication between terms like this, I don't need these parentheses anymore, do I? I can just add this guy and subtract that guy and add that guy. I'm going to move this thing over to the other side. And then I have just these two here. I'm going to move the negative one over to the right, just to make it more convenient. So I'm going to go y times MCl37 minus y times MCl35. We're just doing algebra. Now, since I have something times y in both of these, I could factor it out, right? And that's going to equal this. And then I could divide both sides by this, right? So watch what I'm going to do. This is going to be the magic of Photoshop here. There we go. Division made easy, right? And we can get rid of this. There you go. This whole thing equals y. So now what we can do is we can now fill in the numbers. So let's look for the mass of chlorine-37. Or I'm sorry, yeah, I'm reading the wrong thing and circling the wrong thing. Okay, let's look for the mass of chlorine right here. That's on the periodic table. So we'll grab the periodic table. 35.453 AMU is what it says. So we got that one. Minus the mass of chlorine-35. That's in the problem statement up above that you can read up here. So chlorine-35 has an isotopic mass of 34.9689 AMU. So we got that one. It's divided by mass of chlorine-37. So that's 36.9659 AMU. Got that one. And then this one's just the same thing as above. They don't cancel because that's not how subtraction works, right? There we go. That's going to equal y, which will represent the percentage of whatever y was, which variable it was. So that looks like it was chlorine-37's percent. So now I got to do subtraction, which means that I'm going to the thousandths place in this term, and the 10,000ths place in this term. So you do have to watch out for sig figs. Be careful. 35.453 minus 34.9689. My calculator gave me for the top 0.4841 AMU. But I only get to keep to this position because of this number right here. It only goes to the thousandths place. This number would be subtracted from a question mark. So this gets lost. On the bottom, 36.9659 minus 34.9689. And I got 1.9970 AMU. At this point, the AMUs cancel out because I have units divided by themselves. And so I will get a percentage, 0.484 divided by 1.9970. I have 3 sig figs divided by 5 sig figs. So my answer should be 3 sig figs. So I got 0.24236. Which we're going to report like that. Now that we know what y is, we can then go up here and say, well, I know that x equals 1 minus y. So 1 minus 0.242. So x must be 0.758. When you were subtracting or adding, you do the work and then you do the rounding, yeah. So wherever it rounds to the correct place. So we said that X was, which isotope was X here? X was chlorine-35. And there is 75.8% abundance of that. We said that Y was chlorine-37, and there was 24.2% abundance of that. There you go. So that's how you determine the percent abundance for an isotope pair using just the masses that are given and the periodic table. Which, as you can tell, is super obnoxious, right? So, I mean, it's just algebra, right? So why should we do algebra when we know how to do algebra? Let's make someone else do it. So I need to minimize this because I need to be able to see the equation that I'm working with here. Now, when you do this, you do need to enter, I'll put it down here, I guess. You need to enter the numbers into the expression. And so here's how we're going to do that. So remember that the expression was mass of chlorine, which I'm going to type in. Oh, it's not 9, it's a 3. Equals percent abundance of chlorine-35, I'm going to call that X, times the mass of chlorine-35, which was 34.9689, plus percent abundance of chlorine-37, Y, times its mass, 36.9659. I hit an 8 for some reason. So that's the first equation. And then I'm going to go semicolon X plus Y equals 1. Enter. And let's see what Wolfram Alpha gives us. I'm just cropping down to this so I can go like that. How did we do compared to Wolfram Alpha? I would say that we did pretty good. But look at all the algebra that we had to do. That's bollocks, right? Who wants to do algebra, right? Make a computer do it. So, the only reason I'm showing you the algebra is because I want you to know how to do the algebra. But once you've done the algebra, it's an online class. Put it in a solver. Algebra is great for understanding, but you need to know what it is that you're solving for. So I have to make you do the example once. Once you know, oh, okay, I'm solving a system of 2 equations, then you can go to Wolfram Alpha and type in any system of 2 equations that you want to. And just make it solve it, and that's fine. I'm not going to know. All right, so now what we're going to do is I'm going to go to the next practice problem, and I'm going to have you... Oh, there isn't one. Where is it? I thought I had another one in here. Oh, I do, but it's an easy one. Okay, whatever. Okay, well, if you saw another problem like this, you could do it. I forget if there's one on the... There is a mass spec problem on the quiz. I just forget which type I put on there. But if you get one where you have to solve for percentages, just throw it in a solver. Save yourself some time. If you want to, you can do the algebra. That's fine. Like, I can do the algebra in like 2 minutes, but if it's your first time, it might take 10 minutes or more. So, there you go. All right. How does this information get determined experimentally? Like, how do we get these percentages? Like, we could weigh the amount and do the algebra, but is there a mechanical way to do this? And the answer is, well, if we use the mass spectrometer and we just scan for every isotope that's possible, we can calculate a ratio versus a standard. For example, if I just put in a sample of 100% carbon-12 and hit the button and it analyzes it, it will know how many impacts to expect and call that 100%. If I put in other samples, they're not going to be 100%. And we can compare the intensity on a graph. So it would look like this. This is zirconium. Zirconium has 5 stable isotopes. And on the graph, you can see that for each mass that has a stable isotope, a relative abundance was detected. What that means is that for 100% of the sample that I put in, half of it hit the detector when I had it tuned for zirconium-90. Like 10% of it hit the detector for zirconium-91, about like 17 or so for zirconium-92, and so on and so forth. So by using this technology, we can figure out the percent abundance based on all the ratios of everything else. So the important things here are to note that wherever this falls on the y-axis, that's the percent abundance. And that the number of peaks that you see I don't know how to spell peaks, apparently. I really wanted to draw an E or an S, but my hand wanted to draw an E. Number of peaks is the number of natural isotopes that occur for that element. You will not scan synthetic isotopes doing this because they won't last long enough. For most cases, like if you made a batch of technetium and immediately threw it in the mass spec, then maybe, yeah, it might stick around. But if you're going out looking for different isotopes of, like, say, oxygen, and you just catch like a gallon of air and then feed that into the spectrometer, and only detect oxygen somehow, like maybe it goes through a filter or something, you won't see anything special in there other than naturally occurring isotopes, because your sample size is just very small, and the odds that you would get anything in there are very small, and the detector probably wouldn't pick it up anyway. Okay, so that's how mass spectrometry works. So what I want you to do is, using either algebra or Wolfram alpha, I want you to tell me the average mass of magnesium, and then after you've done that, I want you to compare to the periodic table. Now, the trouble with Wolfram alpha is that it's going to give you infinite sig figs, which you can't keep all of them. And really, the only way to know how many sig figs you should keep is to do the algebra. On Canvas, though, I have to tell you how many sig figs to input, because Canvas doesn't know what sig figs are. So, you know what? Keep as many as Canvas tells you, and use Wolfram alpha. So, I want you to calculate the average mass of magnesium based on these elements you see here. And then what I want you to try and do is draw the mass spec diagram that you saw on the previous slide right here. Okay? You might have to go back in the video or go back to the previous slide to see this. On the y-axis is percent abundance. On the x-axis is mass. It's written as mass to charge ratio. Really, what that just means is that, okay, this is the mass of the thing if it only had one electron removed. So these are all mono ions that were detected. It is possible for the mass spec to detect ions that have been moved, or like if I remove 2 electrons, for example. But then what would happen is it would bend twice as far in the detector and not hit the detector until I went way down to like half this mass. That's more of an advanced topic for mass spectrometry. We're not going to worry about that because it doesn't come up in this class. But when you get to organic chemistry, depending on where you take OChem, if you take it at UW or if you take it at other colleges that use mass spectrometry, that does come up. So just something to keep in mind. All right. Find me an average mass through a calculation of some sort, and then draw a picture of the mass spec output for this. I'm going to go find one, and I'm going to see if it matches what you drew. Okay? So I'll be right back. No, I'm still here. I haven't said anything. I said I was going to go find something, and then I wanted you to solve this problem. Sorry, now I'm like hyper vigilant. Oh, you lost connection. Uh-oh. Is it reporting an error? Can you hear me? Yeah, you can hear me. Okay, cool. Yeah, because I can see the chat, but the chat and the stream are actually... I have it in a separate window. So, like, even if my stream died, I would still get chat, and then I would just be talking to the void. Yeah, I don't have any errors reported. Okay, yeah, if it's just your internet, then just your internet. Okay, I'm going to give you about 2 more minutes, and then we'll go over the answer, because I want to do one last thing before we stop today. Yeah, my internet is fortunately very stable. I have fiber. My speed isn't great. Like, I think I'm using up all of my upload just to get this online. But I've had very few problems, thankfully. Alright, sorry about that. I suddenly got messaged like crazy. Okay. So, I'm going to do the algebra just because it's good to have examples of the algebra online. That's the old example. We don't need that anymore, so we can get rid of that. That's going to get changed anyway. Actually, I want to deal with this a little bit. There we go. Okay. All right, so remember that the average mass of the element that we're going to look at, so its atomic mass, will be equal to the percent of the isotope number 1, so that's magnesium-24, times the mass of magnesium-24, plus percent of magnesium-25, times the mass of magnesium-25. And I've given you all the numbers here, so this is really simple to put in. 0.7899 times 23.985 AMU plus 0.1000 times 24.983 AMU. So I actually have Zip Lead Frontier, and I have never had a problem with it. I did try to update it the other day. I called in and asked, hey, can I upgrade my line? And they're like, yes, no. And it was because like the hardware is ancient or something. I don't know. 18.95 AMU plus, I don't know why I'm putting this one in the calculator. I could just do that in my head. 2.498. So I got hundredths place and thousandths place, so I'm going to end up going to the hundredths place here. Why did I get 20? I punched a number in wrong in my calculator, didn't I? Why did I only get 24? Oh, I know why I only got 24. Whoops. Yep, that's what I thought. I was like, my answer's way too small. All right. So I'm going to add on another term here. I was like, I'm missing part of my sample here. All right. So now I can put in, let's see, 0.1101, 25.983. There we go. That's the missing step. 2.861. And again, down to the hundredths place there. So there we go. That's what I expected. All right. There we go. Okay. Now, what do we do with this? So now we take our percentages and we're going to plot them on a mass spec graph. So I got this percent, and this percent. So I'm going to graph them down here. So I have, that was probably not the straightest line I could have drawn. That's better, I guess. So I got percent, abundance. I'm going to call this 100. So for magnesium 24, down here we'll have mass to charge ratio. Really, oops, that's, there we go. And so I'll say this will be 24, 25, 26, and so on and so forth. I only need to go up to 26, really. So we'll go like this. So, yeah, 80%'s about here. So I'll just do this. And then 10%, these would be really small. Oops, I missed. That's okay. This one will be a little taller. There you go. So I should get something that looks like that. And lo and behold, when I go to this webpage that I found, which is the other really good periodic table site, and I load up web elements, boop. Oh, I did capture all of it. Let's see what it looks like. There you go. Now, you'll notice that it says isotopic abundance on the right side there. That is percent abundance that we got. The top of that is scaled to 78.99%, which is the number that we have reported there. Our graph looks very much like that. So we're all set. All right. Any questions about mass spec, let me know. Happy to answer them. Mass spec was actually like my entire graduate career. Was I just sat in a room doing mass spec on stuff and hoping that it was what I wanted it to be. That and NMR, and then organic synthesis. So like, I guess I've done a lot of things, to be honest. But I know a lot about mass spec, so I could go on and on and on and on and on about it. And that's why I like to introduce it to you here. I don't know if other instructors cover it, but I think it's super cool. I was going to do the last little bit before we start talking about the mole, but I only have 5 minutes, and that's not really enough time, so we'll just do the last bit of Chapter 2 on Tuesday next week, and then we'll start Chapter 6. I realize we're a little behind on the schedule. That's okay, though. We should be good for the exam, which is just 1, 2, and 6. Chapter 6 is not very long, and it's all review from 140, so we should be good. All right, I'm going to put the title card back up. Thanks to everybody for coming out to the lecture tonight. Have a wonderful evening and the rest of your weekend, since I won't see you before then. Again, make sure that you get lab number 1 uploaded before the deadline tonight, because it is due and it will close. And then make sure you take quiz number 1 before the hard deadline on Friday. Try and get it in by the soft deadline if you can. Have a wonderful weekend, and we'll see you next time. Cheers.